Okay.
Please start.
Okay, so thanks for the invitation and thanks for this opportunity to introduce this work at this seminar. Today, I'm going to talk about multiple for homology for three manifolds with toroidal boundary. This is going to generalize the work of Kramer and Morfka for closed three manifolds. This talk will be divided into three parts. First of all, I will explain the motivation of this work and sketch the construction. This project is intended to give an alternative definition of the not-for homology so that the 3+1 Tqft property will follow very easily. And in the second part, I will summarize all the formal properties of this construction that are available so far. And in the last part, I will focus on the analytic aspect and explain the relation of this construction with Landau-Ginzberg models. And let's get started. Let me first remind you on the construction for closed three manifolds. So let Y be a closed-oriented three manifold. Then its multiple for homology is defined by Kramer and Morfka around 2007. This is a topological invariant of the three manifold, and it is quite influential. For instance, you can use this invariant to provide an alternative proof of the Gordon-Look theorem, and also a proof of the Weinstein conjecture in dimension 3. So for the purpose of this talk, let us focus on the reduced version. This is always a finitely generated abelian group. It carries a natural homology grading, and it has another grading by spin C structures. So you can always write it as a direct sum like this. I'm not going to tell you what are spin C structures, but let me just say that if H upper 2 of Y has no two torsions, then the spin C structures on the three manifold are classified by their first chain classes in H upper 2 of Y. So this for homology group has two important properties that we are going to generalize later for three manifolds with toroidal boundary. And let me first give you a brief summary. So the first property here is that if you take the graded Euler characteristic of this for homology, then it recovers the Müller-Churow torsion invariant of the three manifold. This is the case when the first Beatty number of Y is positive. So this result was due to Montaub's in 1996, and it was refined by Churow 2 years later. So on the one hand, for each spin C structure, you can take the Euler characteristic of each summon. So in the end, you obtain a function on the space of spin C structures. On the other hand, this Müller torsion invariant can be computed in terms of some cellular chain complex of the three manifold using a suitable local coefficient system. So it's a classical algebraic invariant, which is pretty nice. Later, we will come back to this Montaub's paper. So the second property here is 3+1 Tqft structure, meaning that whenever you have a four-manifold coborsum from Y1 to Y2, we can construct a coborsum map from the for homology Y1 to the for homology Y2. Moreover, this assignment is functorial with respect to compositions of coborsums. In the end, we obtain a functor from the 3,1 coborsum category to the category of groups. So we'll generalize these two properties later for three manifolds with toroidal boundary. But for now, let me tell you a bit more about the construction. So this for homology is defined as an infinite dimensional Morse theory. In general, these monopole equations or Seiberg-Witten equations can be defined on an arbitrary Riemannian-oriented four manifold. But in our case, we'll focus on this infinite cylinder R times Y, and we pick a Riemannian metric for the three manifold. Then the monopole equations on this infinite cylinder can be interpreted as the downward gradient flow line of the Chern-Simons-Dirac functional. So by running the Morse theory, we take the free abelian group generated by all critical points of this functional, and we define the differential by counting gradient flow lines. We can obtain a chain complex. then its homology is this Floer homology of Y. So the equation that I wrote here is the dimensional reduction of the monopole equations on the three-manifold Y. I'm not going to explain the various expressions in this formula, but I have to point out that there is a way to perturb this equation using an imaginary valued closed-to form on the three-manifold. Okay. And this perturbation will also affect the Chern-Simons direct functional. And this perturbation will play an important role in our construction later. By the way, a solution to this reduction equation is also a critical point of the Chern-Simons direct functional. And when it comes to the cobordism maps, we have to work with a slightly different Floer manifold. So we start with a cobordism, Floer manifold cobordism from Y1 to Y2. We attach a cylindrical can to the incoming boundary and an outgoing and another cylindrical can to the outgoing boundary to obtain a complete Riemannian Floer manifold. Then cobordism maps are defined by counting zero-dimensional solutions of the Seiberg-Witten equations on this space. So this construction is completely analytic, and we have to understand the properties of these monopole equations very well. But this is also the problem, because the monopole equations are usually pretty hard to solve explicitly. So this Floer homology and this cobordism map are usually pretty hard to compute directly from the definitions. At this point, I have to point out another development of Floer homology that uses Hilbert splittings. So these were introduced by Oswald and Szabó around 2001 as the symplectic replacement of gauge theory. And we now know that their invariants are more computable, and these two theories are more or less equivalent to each other. So this is the first advantage. The second advantage is that their invariants can be also defined for not inside a three-manifold. And the simplest versions are the head version and minus version, and they were introduced by Oswald and Szabó and independently Rasmussen around 2003. And it is quite natural to ask what's the analogous construction in the Seiberg-Witten theory. The first attempt toward this direction was made by Kramer and Moravka around 2010, based upon the suture manifold technique developed earlier by Yu Harsh in 2006. So this interaction between Floer theory and suture manifold theory is quite remarkable. But I guess the question is, the problem is if you follow this strategy, then the 3+1 Tqft structure is relatively difficult to verify. So this was only proved by Yu Harsh in 2016 that this suture for homology is a functor from the suture cobordism category. And the similar result was only obtained by Zhengquan last year for its Seiberg-Witten analog. I guess the problem here is that this monopole not for homology is defined in a very indirect way. So one may ask if we can have an alternative definition so that the Tqft property will follow easily. So let me make this question official here. And this is a motivating question for this project. So can we define the monopole for homology for the knot complement by studying the monopole equations on this space? And in general, can we carry out the same construction for any three manifolds with toroidal boundary so that we can verify the Tqft property easily? We are going to answer this question in this talk, and the idea comes from the Montov's paper. So in this picture here, this three-manifold Y has a boundary sigma, and sigma is a union of two tori. And in order to study the monopole equations on this space, the first step here is to specify the metric. So we pick a flat metric of the boundary, and we attach a cylindrical can to this three manifold to obtain a complete Riemannian manifold y hat. So this is a picture for the completion, and we are going to work with a non-compact three manifold. But the first step is not enough. Our second step here is to specify the two-form perturbation here. And in our case, I want to take this closed two-form to have this standard shape, ds wedge lambda plus mu on the cylindrical can. Here, S is the coordinate function for this cylindrical can, and lambda is a harmonic one form on the surface, and mu is a harmonic two form on the surface. And because our metric on the cylindrical can is flat, this two form omega is covariantly constant on the cylindrical can. At this point, we have to make some assumptions on this two form omega. For instance, this one form lambda is non-zero on each component of the surface, and also the cos of hard star of lambda lies in the image of the h upper 1 of y. So there are a few other conditions. I'm not going to give you a complete list, but let me just say that our construction has certain limitations, and the resulting Floer homology group may potentially depend on this closed two-form omega. But I guess this is forgivable. We can still prove something interesting and make some progress. As I mentioned earlier, this idea is not new. I didn't invent it. So this setup comes from this Montauf's paper, and we have already seen this theorem before. It says for any closed-oriented three manifold with B1 positive, the graded Euler characteristic of this Floer homology recovers a torsion invariant of the three manifold. But if you read their paper very carefully, then you realize that their actual statement is much more stronger than this. So the same statement is true also for any three manifolds with toroidal boundary. So this is what happened in their paper. In this Montauf's paper, they worked with this three manifold with cylindrical cans. They worked with this closed two-form omega, and they take the sign count of critical points of this functional as the definition of three-dimensional Seiberg-Witten invariance. At that time, we didn't yet have a Floer homology, but this sign counting is still well posed. And they showed in their paper that this 3D Seiberg-Witten invariance recovers this Milnor torsion invariant. So they only took the first step in their paper. They take the sign count of critical points. But maybe we can go one step further and consider the gradient flow lines of this functional and define a Floer homology. This amounts to studying the monopole equations on this product form manifold R times y hat. And because y hat is already non-compact, this product manifold is now non-compact in two directions, in the time direction and in the spatial direction. And it carries a planar end that looks like the upper half plane times sigma. Here I'm using the Euclidean metric on the upper half plane. And over this planar end, the monopole equations are perturbed by this standard two form. And by counting solutions on this space, we can construct the chain complex and define Floer homology. So this is everything I want to say about the construction. And before we move forward to the next part and state the main result, I should probably pause for questions. So any questions so far regarding this setup from Montauf's paper?
So actually, can you, or maybe we'll say a little bit more about like what kind of decay conditions you're going to impose somehow as you go out to infinity?
Yeah, so in the limit, there will be a standard configuration, which is translation invariant on R times sigma. So there is a standard configuration at infinity. and we want all the configuration to decay exponentially towards that.
I guess I was asking a little, maybe a more about the when you're working on this half plane, you know, the thing that looks like, you know, torus across a half plane. When you're doing the cobordisms, what kind of, yeah, in that step.
Yeah, we still have the same decaying condition, exponential decay towards a standard configuration.
But does it sort of depend on like which direction you go out to? I mean, because there's a sort of a whole plane.
In the spatial direction, in a uniform way. Yeah, uniformly in the spatial direction.
And if you impose like if you input some L2 norm and, you know, finiteness of L2 norm on energy, do you still get the same thing?
I think yes. So our estimate starts with the energy estimate. So if we know some finiteness of energy, then we know the exponential decay. But we have to define the energy properly. Yeah, I will come to that point later. Yeah, in the last part.
Okay.
All right. So let's move forward and state the main result. Just to assure you that our construction indeed works. So this is our main theorem here. It says for any oriented three-manifold Y with toroidal boundary, and for any closed two-form omega satisfying all the properties I mentioned earlier, the monopole for homology of this pair is well defined as a module over non-recovering. Moreover, this group is independent of the interior metric of Y, and it is invariant if we replace omega by omega plus d beta, where beta is a compactly supported one form on this cylindrical and three-manifold. And this for homology also carries a grading by relative spin C structures. So you can write it as a direct sum like this. Here, a relative spin C structure is a spin C structure with a fixed trivialization near the boundary. So their first chain classes now lie in the relative cohomology group of Y. All right, so at this point, there are two potential problems. First of all, in the first statement here, this interior metric of Y really mean the metric of Y over this compact region. And we have to fix the boundary flat metric. The reason is if we change this flat metric, it will change the geometry of this four manifold dramatically. Then we won't be able to define the continuation map. The second problem here is, although each individual summand here is finitely generated over the base ring, this is not necessarily true for this direct sum. For instance, for the knot complement, these summands are non-zero for infinitely many relative spin C structures. But somehow, these two problems can be resolved if we make an additional assumption here. So suppose this 2 for mu is non-vanishing on the surface, then this Floer homology group is finitely generated. And this Floer homology is independent of the flat metric of the boundary. Lastly, this Floer homology will depend only on the cohomology class of omega. So the last statement here is slightly stronger than the second one here. And because of 4 and 5, in this case, we do have a topological invariant for this pair. I think this property, this condition is really convenient to work with, but there is also a price to pay. Because if such a 2 form exists on the 3 manifold, then the boundary of Y is necessarily disconnected. Because mu is the boundary value of this 2 form omega, and omega is closed. So its integral on the boundary is necessarily 0. But I think this is not a serious problem in practice, because in order to recover the knot Floer homology, we will actually work with the link complement. And let me make this more concrete. So let's take a knot inside a closed 3 manifold Z, and this is a picture, and we also take a meridian for this knot. Then we want to apply our construction to the complement of this meridian and this knot. Now the boundary is disconnected, and if we choose the closed to form omega carefully on this space, then we can recover the knot for homology. The argument works as follows. So this meridian bonds a disk inside the closed 3 manifold, and this disk becomes an annulus in the link complement. And let's call it A. And if we cut along this annulus, it's like a suture manifold decomposition. We can obtain a balanced suture manifold with 2 meridional sutures oriented in the opposite ways. And the knot for homology of this knot is defined as the balanced suture of the suture for homology of this balanced suture manifold. Okay. And we can show that this cutting process will not affect the full homology group. So in this way, we can recover the knot for homology. But here we have to choose this closed to form omega properly. And just in case you are interested in the choice of omega, for the Poincare dual of the class of Hodge star of lambda, we will take it to be the boundary of A as one cycle on the surface sigma. And for the class of the Poincare dual of the closed to form omega, we'll take it to be an arc lying over the annulus. Anyway, so this is just a small technical detail. And with this choice of 2 form omega, we can recover the knot for homology. So this is our first result. We do have a nice for homology. The second thing I want to say is the Tqft structure, as I advertised earlier. In this picture, each 3 manifold Yi is the 3 manifold with boundary. So a coborism is necessarily a 4 manifold with corners. And this horizontal manifold W is a coborism from sigma 1 to sigma 2. And such a coborism is called strict if this horizontal manifold is a standard product. So this is, of course, very restrictive, and it forces sigma 1 to be identical to sigma 2. But under this condition, we can indeed construct this coborism map from the full homology of the first pair to the full homology of the second pair. And again, this coborism map is constructed by counting solutions. So we start with a 4 manifold with corners. We first attach cylindrical ends in the spatial direction. Then so after this attaching, we have a coborism from Y1 hat to Y2 hat. Then we attach 2 cylindrical ends in the time direction. And in the end, we have a complete Riemannian 4 manifold. Then by counting 0-dimensional solutions of the separating equations, we can construct this coborism map. So of course, we are not really happy with this result, and we really want to remove this condition. And to do that, we need to first introduce a gluing theorem. So in the picture here, each dot represents a surface sigma I, which is a union of 2 tori, and is equipped with a harmonic 1 form and a harmonic 2 form. And each segment here represents a 3 manifold coborism between them. And whenever you have 2 such coborisms, you can take the composition to obtain a coborism from sigma 1 to sigma 3. The conclusion is we can construct a map alpha from the tensor product of the Floer homology of each factor and end up with Floer homology of this composition. And if we assume in addition each mu I is non-vanishing on the surface, then this map is also an isomorphism. This is the content of the gluing theorem. So here is a caveat. So this gluing theorem is not as general as you may expect, because when two such three manifolds are glued along sigma 2, their two forms have to agree with the standard form on the boundary. This imposes a non-trivial condition on the way they are glued together. I don't really have time to explain the construction of this gluing map alpha, but it's not mysterious. And the construction is inspired by Floer's excision theorem. So it turns out to be quite elementary and effortless. So, but now let us move on and construct the generalized cobordism maps. So in general, if we don't make any assumption on this horizontal manifold, then we can construct a map from the tensor product of Y1 and W and end up with the Floer homology of Y2. Okay. So in some sense, the Floer homology of this horizontal manifold is parametrizing all possible cobordism maps we can obtain from this picture. So how is this map constructed? So the idea is to smooth the corner along sigma 1. And after this smoothing, we can obtain a copy of Y1 circ W. So our first map here is our gluing map alpha. And if you look at the rest of this cobordism, it now becomes a straight cobordism. So our second map here is given by our previous construction. I think this idea of smoothing corners goes back to Juhas in his construction of suture cobordism maps. And I'm using the same strategy. And of course, this is not going to give us a standard Tqft if I state it this way. But there is a different point of view. So if we instead define a morphism as a triple, where x, comma w is a cobordism like this, and A is the element in this Floer homology group, then we can recover an ordinary 3+1 Tqft, meaning an ordinary, a genuine functor from a cobordism category to the category of groups. But here, in order to make sense of compositions of morphisms, you really need this gluing map alpha here. So we do have a Tqft structure in this case. And the last thing I want to say is a Thurston norm detection result. And such a result is classical for closed ring manifolds. And in our case, we'll work with a three manifold with toroidal boundary, and we assume Y is irreducible, and the boundary of Y is disconnected, because I really want a 2 for mu that is non-vanishing. Our first statement here is that this group is non-zero. But in order to see the Thurston norm, we need the grading information. So let us look at the space of spin C structures for which these summands are non-zero and their first chain classes. So this is going to be a subset of the second relative cohomology group of Y. And let's consider the function defined on the dual space. So phi of kappa is defined as the maximum of all such pairings, where A is a monopole class, and kappa is an element in the dual space. The conclusion is the Thurston norm of kappa can be recovered as the symmetrization of this function phi. So here, there are two additional remarks. First of all, any three manifold with toroidal boundary can be realized as a link complement for some link inside a closed three manifold Z. And we already know that the link for homology detects the Thurston norm of the link complement. So this result was due to Oswald-Szabó and Ni when the three-manifold Z is a rational homology sphere. And the general case was due to Yu-Hash. And a similar result was obtained by Zhengkun and Ghosh last year for the Seiber-Witten analog. But the problem is that, so for a given three-manifold Y, there are many different ways to realize it as the link complement. So there are many different ways to do Dunn-Field links. And the statement of their detection results will reflect the choice of this pair. But on the other hand, our statement here is more intrinsic. It doesn't really rely on the closure of the of this three-manifold. So yeah, that's why I think it's slightly better. But anyway, the second remark is this detection result is not the most ideal version. The ideal version would just say the Thurston norm of kappa equals phi of kappa. And the problem here is that I cannot verify that this set of monopole classes is symmetric about the origin, or this function phi is an even function. And I hope we can improve this result in the future. And finally, just a word about the proof. The argument is very elementary. So we use the gluing theorem to reduce, to relate the Floer homology of this three-manifold Y with the Floer homology of the double. So we take the orientation reversal of Y and we glue them along their common boundary to obtain a closed three-manifold. Then the gluing theorem will allow us to reduce this detection result to the case of closed three-manifolds, in which case the result is well known. So this is everything I want to say about properties. To summarize, our Floer homology categorifies the mu-neutral of torsion invariant. It has a pretty nice Tqft structure, and it detects the Thurston norm when the three-manifold is irreducible and the boundary is disconnected. And let me pause for questions.
I wanted to ask about if it's possible to compare your invariant under like a change of that perturbation, right? Like, because lambda kind of encodes the meridian in some sense. Like, if you change the meridian to you know, a different class, right? So it measures, let's say, like the dual knot of after surgery. Like, are you able to use your generalized cobordism maps to like compare the different variants under the different perturbations?
This is a great question, and this is the main limitation of our construction. I don't understand the dependence of our group on this two-form omega, on the class of omega and on the class of hard star of lambda. So there are two classes we have to choose, and I don't understand the dependence. This is a great question, but I don't know how to answer that.
Okay, thanks.
Is there any relation between your cobordism maps and cobordism maps in structured monopole Floer homology?
I don't really know how to answer that question. I would wish there is a good relation. But I think the heuristic here is that in suture cobordism category, you usually pick up a contact structure on this horizontal manifold. So somehow, in our case, if you pick up a contact structure, maybe you can also define a contact element here. And if you make A to be the contact element, then this structure is pretty similar to the suture cobordism picture. But so far, I don't know how to define a contact element.
So, okay, just to make sure that I understand it correctly, so you have a cobordism map from the tensor product of monopole Floer homology of Y1 and monopole Floer homology of W, and you're saying that if you insert the contact class for W, from that part, that should give you the cobordism map in suture, sorry?
very similar. I think they will have a very similar structure. But I guess another point is we cannot really recover suture for homology. So there is an analog, but they are not really the same thing.
Okay.
So are there any other questions?
One more.
Mm-hmm.
So you said you can get not homology, right?
Mm-hmm.
Monopole, not homology, using that. And then the natural question to ask would be, if you have a cobordism that from one manifold to another with a knot and a surface that bounds the two knots, do you
Mm-hmm.
What do you get in this picture if you start with that? Do you get some maps?
Well, so I guess this is a great question. And I think the next interesting question is compare this Tqft structure with the decorated link cobordism picture. And the idea is when you have a surface bounding two knots, the way you construct the cobordism map is you pass to the normal bundle of that surface. So this horizontal manifold W is going to be the normal circle bundle of the surface. And we do know how to compute the full homology of this guy. So this is a genus G surface with n punctures. But as I mentioned earlier, I don't know how to define contact elements. So in decorated link cobordism categories, usually you have some decorations on the surface, and these decorations will pick up contact structure on the normal circle bundle. And then you use that element to define the cobordism map. So I think our next step is to define the context element and try to compare this construction with the decorated link cobordism picture. This is a good question. This is going to be the next step. Thanks.
Okay, thanks.
All right, so let's move forward to the next part. So for the last part of this talk, I will discuss the analytic aspect of this construction. There are many analytic details we have to work out, and I will focus on one of them and try to explain why this closed two form omega is necessary for the construction, and why Landau-Ginzberg models are useful for the proof. So the first observation here is that if you work with this standard cylinder R times sigma, and if you work with this covariantly constant standard two form omega, then the three-dimensional separating equation has a unique R invariant solution on this space. Let's call it gamma star. And this configuration is irreducible. So this observation, I think, was due to TOPS, and it is essential here to assume one of lambda and mu is non-zero. Otherwise, the statement is wrong. And when it comes to a three manifold with cylindrical cans, we'll require each solution to approximate this standard solution gamma star at infinity in the spatial direction. So in some sense, we are imposing some finiteness condition on the energy. And when it comes to a four manifold, so for a four manifold with a planar end, we will also require each solution gamma to approximate this standard configuration along the spatial direction. But the problem may arise if we consider a sequence of solutions to the monopole equations. Then maybe some amount of energy will eventually slide off along the cylindrical can and converge to a finite energy solution C times sigma. And such a finite energy solution is usually called a point-like solution. So the problem here is that although each individual solution will converge to the standard configuration in the limit, but maybe this convergence is not uniform. And if this divergence phenomenon happens, then we are in big trouble, because the differential we defined in the usual way may not have square equal to 0. And we really want to, so our goal here is to rule out all possible point-like solutions. And this goal is achieved by the next theorem. So the problem I just described is completely local. So we can assume our surface is connected. And if in addition, this one form lambda is non-zero, then any finite energy solution on this product form manifold is necessary gauge equivalent to the trivial solution, which is translation invariant in 2 directions and whose energy is identically 0. So here, the monopole equations are perturbed by the standard 2 form on this space. So there are 2 additional remarks here. First of all, you may wonder what will happen for a heterogeneous surface. And in that case, if we still assume this one form lambda is harmonic, and the 1, 0 part of lambda has 2g minus 2 simple zeros, then theorem A is still true. So in this case, maybe we can still define the Floer homology when the genus of the boundary is greater than 1. The second remark is this triviality result is not really trivial as it appears, because it really relies on this assumption. And interesting solutions can exist if we know lambda is identically 0. And in this case, in fact, we can classify all point-like solutions on this standard, on this product form manifold, but still we don't really want to work with them. It will break the compactness result. So theorem A is apparently the foundation of our construction, and for the rest of this talk, I wish to explain some ideas hidden behind this triviality result. The statement of theorem A doesn't involve Landau-Ginzberg models, but they appear quite naturally in the proof. And it is really the structure hidden behind everything. But first, let me remind you the definition of LG models. A Landau-Ginzberg model is simply a pair where M is a complete non-compact Kähler manifold, and W is a holomorphic function defined on this Kähler manifold called superpotential. And an LG model is called Morse if the real part of the superpotential is a Morse function. And the simplest example is when M is Cn and the superpotential is the sum of squares. This is the definition when the dimension of M is finite and when the structure group G is trivial. And we are going to generalize this definition later. A Morse LG model is also a Lefferts vibration. And the benefit is the Foucault category of Lefferts vibration is usually much easier to understand because we can work with symbols. So a symbol is simply a stable submanifold or unstable submanifold of a critical point of the real part. So the upshot is a symbol is always a Lagrangian submanifold of the Kähler manifold M. And the Foucault, and if you consider all critical points of the real part, then the Foucault category of M is generated by all these symbols in a suitable sense. The Foucault category or Lagrangian homology groups are defined usually by looking at the Floer equation, which is simply the Cauchy-Riemann equation defining this infinite strip. But here, I want to perturb this equation using the imaginary part of the superpotential. So in general, you can use any Hamiltonian function to do the perturbation. But when it is the imaginary part of a holomorphic function, this equation has a richer structure. For instance, lambda h is also J of lambda L. J is the almost complex structure. So the gradient of the real part is also the Hamiltonian vector, the great Hamiltonian vector of the imaginary part. And also, I want to study this equation instead on the complex plane or the upper half plane. At this point, you may ask, so why do we want to study this equation on the upper half plane? So is there any geometric meaning? So the motivating question here is, if we take an arbitrary Lagrangian submanifold in this scalar manifold, how do we define the Lagrangian for homology of this pair L along with this symbol S star? Traditionally, this is done by counting holomorphic strips with Lagrangian boundary conditions. And suppose here we work with this perturbed equation, and we look at time-independent solutions. So the time derivative is identically 0. Then a solution is simply a piece of downward gradient flow lines of the real part. And this flow line starts at somewhere on the Lagrangian L. But the point is the other Lagrangian S star is the stable submanifold of the critical point. This means we can also continue this flow line until in the limit it approaches this critical point of the superpotential. So this picture is suggesting that maybe we can also define this for a homology group by counting holomorphic upper half planes. So over this space, we are going to consider this perturbed equation. And also on the real line, we have Lagrangian boundary condition. But on the other side, we will require our configuration to approach this critical point of L in a uniform way. We have already seen that these two formalisms will give us the same set of generators for the Floer chain complex. And the heuristic is they should also give us the same for homology groups. And the second formalism is somehow the toy model for our monopole Floer homology. So the first formalism is classical, it's good, but it is hard to generalize when the dimension of M is infinite. So let's come back to LG models. Now we have a definition and we have an equation, and we wish to generalize them when the structure group G is non-trivial. And then we obtain a gauged LG model. A gauged LG model is now a triple, where M is again a complete non-compact Kähler manifold. The compact Lie group G acting on this acting on M will preserve the Kähler structure. This action is also required to be Hamiltonian, admitting a moment map. And the superpotential now is the G invariant holomorphic function. The simplest example is when M is the complex plane. G is S1 with the standard circle action, and W is identically 0, and the moment map is essentially a quadratic function. And our next step is to generalize the Floer equation. And now it is stated for a pair A, P, where A is the connection on the trivial G bundle over the domain C, and P is a smooth map from C to the Kähler manifold M. But you should really regard this smooth map as a section of the trivial M bundle over the domain. So whenever you take derivatives, you should really take covariant derivatives. So now the Floer equation is coupled with the connection A. And there is an additional equation relating the curvature of A with the moment map. And this system of equations is called the gauged weighting equations. And for this example here, the gauged weighting equations will recover the vortex equations studied by Professor Tqft about 40 years ago. So we understand the properties very well. So later we'll see that the gauged weighting equations are like the universal equations. You can plug in different gauged LG models and you can obtain different equations in gauge theory. There are two more things I want to say at this point. First of all, what's the replacement of the Morse condition? For instance, you can ask the restriction of the real part on the symplectic quotient is a real valued Morse function. But this is not a strong condition in practice. And the right replacement is the notion of stability. I'm not going to give you the precise definition here, but somehow we wish to extend the action of G to the complexified structure group. And this stability is stated in terms of this complexification. The second thing I want to say is the notion of energy. So in this case, the energy is simply defined as an integral of a few L2 terms, L2 norms. And let's think about the consequence. So we have already seen all these terms in the gauged weighting equations. So what will happen if we know the energy is identically zero? Then it means first of all, the connection is flat. So up to gauge, this connection is trivial. Also, this smooth map P is constant with image lies in the fiber of the moment map and the critical locus of L. So there is a very concrete geometric meaning for zero energy solutions. Okay, so we have a very similar setup in. We have a very similar situation as in Theorem A. We have an equation and we have a notion of energy. And we can ask, can we find any non-trivial solutions on the complex plane with finite energy? And this question is answered by Theorem A prime. So suppose our gauged LG model is stable, then any finite energy solution to the gauged weighting equations on the complex plane is necessarily gauge equivalent to a constant solution with zero energy. Moreover, such a solution is translation invariant in two directions. So Theorem A prime is already similar to Theorem A, and their relations are explained by the following lemma. Suppose our surface sigma is connected, and we take any harmonic one form lambda, then we can construct an infinite dimensional Landau-Ginzberg models such that the several weighting equations on the C times sigma perturbed by the standard 2 form is equivalent to the gauged weighting equations on the complex plane. Moreover, under this identification, the special solution gamma star is identified with this constant solution with image in this intersection. Lastly, this infinite dimensional LG model is stable if and only if the one form lambda is non-zero. So using lemma B, you can reduce Theorem A to Theorem A prime. So the only difference is in Theorem A, the dimension is infinite. So we have to specify the Sobolev norm for the Kähler manifold to produce the right topology. But otherwise, the proofs of Theorem A and Theorem A prime are identical. So this is everything I want to say about the proof. I think this relation between the several weighting equations and gauged weighting equations are probably not well known before. And this is really the point I want to make for today's talk. But I also think maybe this picture should also have other consequences. So let me give you a proposal here. So recall that a Morse LG model is also a lattice fibration. So by the work of Paul Seidel, you can construct the Foucault category of this lattice fibration. And this Foucault category is generated by a bunch of symbols. So the long-term goal of this project is to construct the Foucault category for these infinite-dimensional Landau-Ginzberg models. Moreover, for any three-manifold Y1 with boundary sigma, we want to construct an N-infinity right module over A. And for any three-manifold Y2 with boundary, whose boundary is the orientation reversal, we want to construct an N-infinity left module. Eventually, when Y1 and Y2 are glued along their common boundary, we want a gluing theorem to help us recover the full homology of this closed three-manifold. So the gluing result I mentioned earlier is for the case when mu is non-vanishing everywhere. And in that case, this Foucault category is somehow trivial, so we simply have a tensor product. But the case when mu is identically zero is more mysterious, and we don't really know too much about this case. And this is going to be the next step. I think the main difficulty of this proposal is that when the dimension is infinite, it is not convenient to work with Lagrangian boundary conditions. And there are at least three works that I want to point out in this direction. So, the study of infinite-dimensional lattice fibrations has been pioneered by the work of Andrew Hedges and the work of Gato Moore-Witten. But they have a slightly different application in their mind. In their case, this scalar manifold is the space of SL2C connections on a closed three-manifold, and this superpotential is the complex valued Chern-Simons functional. Then the gauged weighting equations will recover the Hedges weighting equations on the five-dimensional manifold C times Y. And this idea even goes back to the work of Donaldson Thomas, in which case they considered a complex vector bundle over a Calabi-Yau threefold. And this scalar manifold M is the space of D-bar operators on E, and W is the holomorphic Chern-Simons functional. Then the gauged weighting equations will recover the spin 7 instanton equations on C times Y. And in their papers, they proposed various ways to construct the Foucault category in this infinite-dimensional setup, but none of them actually work in practice because of the fundamental compactness issue of their equations. But the separate weighting equations usually have a pretty nice compactness property. So my proposal here is that we should take the separate weighting equations as the field test for their programs in higher dimensions. So to summarize, whenever we have a Morse real valued Morse function manifold, we can define its Morse homology. Its infinite dimensional analog is the Morse theory. And when we have a holomorphic Morse function on Kähler manifold, we have the Pinker-Lefschetz theory. Then what's the infinite dimensional analog of that? And I hope we can fill in this blank in the future, at least for separate weighting equations. That's all I prepared for this talk, and thanks a lot for your attention.
Thank you very much. Are there other questions?
I was wondering, for your gluing theorem, let's say you're working, you have two three manifolds, each with a single boundary component being a torus, and with, let's say, mu and lambda non-zero, and you like try to glue them together and like try to splice together like the Floer homologies of the two guys, right? What do you think you'll recover in terms of its relationship to the ordinary monopole Floer homology of the closed manifold together?
The first point is, so if the boundary of Y is connected, then the 2 for mu is necessarily 0. And in that case, we don't yet have a gluing theorem. So our gluing theorem applies only for boundary, disconnected boundary. And so when mu is identical, when mu is non-vanishing everywhere, we simply have tensor product. So let's write. So let's say y can be recovered as the composition of YL and YR, and our gluing result is saying that the monopole for homology Y can be recovered of this tensor product. The general case is if mu is 0, we would expect there is a special sequence from this tensor product to the monopole for homology of this closed 3-manifold. This is the expectation, but we don't know how to verify that. Does this answer your question?
Okay. Maybe. I'll think about it. Thanks. Appreciate it.
Is there some way to get around this boundary being connected, like for that exactly the problem you mentioned, that you would need mu equals 0 by essentially just like puncturing the 3-manifold and remove a ball, and then I guess maybe I had the wrong, maybe that's not going to work. Yeah, okay, so never mind.
Yeah, I don't know. So for instance, for any closed 3-manifold, you can take an unknown and you remove the neighborhood of this unknown.
Yeah, maybe that would be more appropriate.
You can ask what's the relation of this for homology with the version of closed 3-manifold. And I don't know the answer. It's a good question, but I don't know. Yeah. It would be very interesting if there is a formula.
So for mu equals 0, you do have a definition of the homology groups?
Yes.
Okay. So
yeah. So the heuristic is so A infinity modules are somehow A infinity functors from A infinity algebra to the A infinity category of chain complexes. So for each A infinity module, there is an underlying chain complex. So, and we have constructed the underlying chain complexes, but we don't have the A infinity structure. That's the problem. I hope we can define the A infinity structure in the future.
I have a slightly more out there question, but I guess, do you think there is a more maybe geometric picture of what you think this A infinity action should be in the setting? Like, instead of thinking about it in terms of Tqft categories and like the Landau-Ginzberg model, just like in terms of monopoles on the surface across C.
Well, I guess that's going to be a project to figure out the geometric meaning of this A infinity structure. So eventually, I think this A infinity structure will be constructed in a geometric way, like counting some solutions on more complicated 4-manifolds. But I just don't know how to do that yet.
Okay.
Yeah.